So let's take a look at some area with sums and limits. An introduction to Calculus 2. Now, this is just a triangular region over here, so the area is pretty straightforward. We're just going to look at it a little bit different. So we're going to set up a sum. So one way to set up a sum here would be to just mimic this area with a bunch of rectangles. So for example, we could break this up into rectangles, sort of like this. And this is a helpful technique for curves. And we're going to do it for the straight line segment because it's one of the easiest examples we can take a look at. So this would be an approximation of this area using right-hand endpoints. It's an upper sum because all of the rectangles are a little higher than the line. So to set up something like this, I need a couple of pieces of information. One would be what is the function. So in this case, I have f of x equals 2x. And I need an interval to look at. So this is going to be on the interval from 0 to 1. It's helpful to know how to choose endpoints, and so we're going to use what's called right-hand endpoints. And how many intervals to make. And so we're going to let n equal 5 at first. So to figure out how wide each rectangle is, that's what we call delta x, change in x, and that's just going to be the width. 1 minus 0 is 1 over 5. 1 over n, so in this case 1 over 5. And the beginning of the interval, x0, that's the 0 in this case, but it could be any number. And then the first x value I would grab after that, x, that's a 1 there, would be 0 plus 1/5. And then the next one would be just to keep adding 1/5. So it'd be x equals 1/5 plus another fifth, so I'd get 2/5. So this works out pretty nice. And I just keep repeating that process. I'm going to generalize this a little more, and just to ignore that I said n is 5. So in general here, starting at 0 in this case, I'm just adding on 1 over n. So the smaller I make the rectangle, the more rectangles I make in that region, the better the approximation is going to be. So then the second one would be to take the previous one, 1 over n, add another delta x to that. So 1 over n plus 1 over n is going to be 2 over n. And then I'm going to add another 1 over n to that. And so the third one is going to be 3 over n. Then I can kind of generalize it. So somewhere down the road, I'm going to have this position I. So x sub I is going to just be equal to I over n. So then any particular rectangle is going to have a base and a height. The base of each rectangle in this case is my delta x. And it's going to have a height. The height is determined by the function value, where you plug in whatever you discovered your x pattern is. So in this case, I'm just going to plug in my x value here to my function. That means I'm going to have 2 times my x value. My x value happens to be I over n. Putting that all together, with my delta x being 1 over n, my height being 2 times I over n, I can get a sum. So I'm going to add up all of these rectangles, and a rectangle has a base 1 over n times the height 2 times I over n. And I gets to range I have right-hand sums starting with 1 and ending at n. Because I chose to have n rectangles. N could be 5, but in this case, I'm just letting it be n. Now, the variable in this summation is I. N is a constant. It could be 5, it could be 10, it could be 100. Constants can be pulled out of sums. So 2 is a constant and n is a constant, so I get to pull out a 2 over n squared. And that leaves me in the sum, as my variable of the summation goes from 1 to n, I'm just adding up I. That's going to give me 1 plus 2 plus 3 and so on, all the way up to whatever n is. Now, this may be a formula you've seen before. I'm not going to prove it right now. I'm just going to state that if you try to add the numbers from 1 to n, which is what this says to do right here, all the way up to n, shortcut for that is whatever n is times n plus 1 over 2. So my sum, which is approximating the area, was 2 over n squared times this sum above, and that sum evaluates to n times n plus 1, all over 2. Now this cleans up a little bit. 2 divides into 2, n divides into n. So this tells me the area, given n rectangles, is going to be n plus 1 over n for this particular function. Every function is going to be a little bit different. Now, a cool thing about being able to simplify this and get rid of the summation and get it down to an algebraic formula like this is I can now take the limit as n goes to infinity of this right-hand sum. So we usually refer to that as r sub n. So I have the limit as n goes to infinity of that sum as I was going from 1 to n. And I had, remember, my base was 1 over n. My height was 2 times I over n. And it turns out that cleans up to be just n plus 1 over n. Oops, I missed something there. I missed my limit. Let's move that over a little bit. Nope. Let me move the whole thing. Maybe, maybe not. All right, maybe not. So we'll rewrite that. So I have the limit as n goes to infinity of n plus 1 over n. And in the limit, hopefully remember your limit rules, that just comes out to 1 in the end. So if I used 5 rectangles or 10 rectangles, I'm going to get roughly what the area is. So for example, my formula tells me that using 5 rectangles with right endpoints, I'm going to get 6 over 5 as the approximate area, which would be 1.2. If I tried to use 10 rectangles, I'm going to get a better answer. That's going to be 11 over 10, which would be 1.1. And I could keep using more rectangles and getting closer and closer, but what I found is that the actual area, because I could take the limit, is 1. If we look back at the picture here, I have a base of 1 here, I have a height of 2, and the area of a triangle is always 1/2 times the base times the height. So that gives me that area of 1, which I calculated previously. So this is the idea called the definite integral. And the definite integral is this whole process right here. So the integral from some starting value a to some ending value b of a function f of x dx is equal to the limit as n goes to infinity of what we call a Riemann sum. And there's many kinds of Riemann sums that you can make. I chose one with right-hand endpoints, but you can have left-hand endpoints or midpoints, and there's many, many other options. But the bottom line is you're going to have some delta x, that's your base of each rectangle, and you multiply delta x by some function value where you pick an x value in each interval, and those are called your xi stars. If this limit exists, then you have what's called a definite integral. So specifically in this case, we found that the integral from 0 to 1 of 2x with respect to x was equal to that limit on the previous page. That would be this right here. So that was the design of my Riemann sum. And in the limit, we found that had an area of 1. Now, creating these sums is a lot of work, and simplifying the summation so you can take its limit, that works sometimes, and other times it's really hard or impossible to do. So our goal next is, now that we have the idea that an area can be a sum, the limit of a sum gives us an integral, and an integral tries to give us the exact area instead of just an approximate area. What we're going to try and do is trying to find some other ways to get from here to an answer. So that will be next up. Take care. Do good math.